Biochemistry 401 Lecture 19. Today we're going to talk about the pyruvate dehydrogenase complex. This is a complex that forms acetyl coenzyme A for entry into the TCA cycle. This is a multi-protein complex that includes 3 enzymes and 5 cofactors. We're going to talk about the proteins themselves, the cofactors, and key concepts. We're specifically going to talk about key reactions and regulation. And so this is a schematic of where we're going. We're going to take fatty acids, glucose, and amino acids, and we're going to turn those into acetyl-CoA. This is an activated 2-carbon molecule that can enter the citric acid cycle. Now, the purpose of the citric acid cycle is to oxidize this fuel source to generate 8 electrons that can be passed to the electron transport chain to generate a proton gradient. This proton gradient results in the production of ATP from ADP, an inorganic phosphate. This process, in 2 steps, the electron transport chain and the formation of ATP by the proton gradient, is known as oxidative phosphorylation. As the name implies, this is an oxygen-requiring process. 2 carbons from each pyruvate molecule will enter the TCA cycle to be oxidized. The 3-carbon pyruvate must be decarboxylated, and the resultant 2-carbon product, an acetyl group, is also activated by coenzyme A. And so the final product, acetyl-CoA, condenses with the 4-carbon oxaloacetate to form a 6-carbon molecule citrate, and this begins the cycle. Now, the TCA cycle is actually at the center of metabolism. It is one of the most important pathways that you're going to study this semester. This cycle harvests energy through the oxidation of acetyl groups to yield 2 molecules of carbon dioxide and high energy electrons for the electron transport chain in order to fuel the production of ATP. It also serves as a source of building blocks for anabolic reactions that make fatty acids, amino acids, nucleotide bases, porphyrins, and glucose. Fatty acids can be made from the metabolite citric acid, and citric acid is also important for the regulation of fatty acid synthesis. Amino acids can be made from alpha-ketoglutarate and oxaloacetate. Nucleotide bases can be made from alpha-ketoglutarate and oxaloacetate as well. Porphyrins, as we saw, require succinyl-CoA as a reactant. And the formation of glucose, as we saw with gluconeogenesis, can use oxaloacetate as a starting metabolite. And so the TCA cycle is extremely important for 2 main reasons: for harvesting energy and as a source of building blocks necessary to make macromolecules. And so now we're going to look at the process that is shaded in yellow, going from a 3-carbon pyruvate to an activated 2-carbon molecule, acetyl-CoA. The strategy behind making acetyl coenzyme A is that the thioester bond that links the sulfur and carbonyl group is at a higher energy because there is no resonance structure that stabilizes this thioester bond as there is with the regular ester linkage. And so when you transfer this acetyl group from a thioester to the normal ester, the difference in energies helps to drive the reactions forward. And so coenzyme A is often used as a carrier of acyl groups. So how do we make acetyl-CoA? This is really complex. We do this by using the pyruvate dehydrogenase complex. This is a huge enzyme complex, actually, and it has multiple copies of 3 individual enzymes. And so we don't just have a complex of 3 enzymes. We have a huge complex of multiple copies of each of these three enzymes. The enzymes are E1, E2, and E3. Now, these are not the same ones that we saw with ubiquitination. However, they were referred to as E1, E2, and E3 just for purposes of brevity. The actual name for E1 is pyruvate dehydrogenase. The name of E2 is dihydrolipoyl transacetylase. The name for E3 is dihydrolipoyl dehydrogenase. You will need to know the names of these enzymes, both as E1 and as pyruvate dehydrogenase, dihydrolipoyl transacetylase, and dihydrolipoyl dehydrogenase. This is because the names help to drive home the reactions that these enzymes catalyze, and for that reason, I would like you to learn these. Below, we see an electron micrograph that shows several pyruvate dehydrogenase complexes. We see each individual complex being made up of individual subunits that look like little soccer balls. Again, each mitochondrion has many dehydrogenase complexes. It is important that you know the columns that are highlighted in this table. Again, you need to know the enzyme and the abbreviation. You need to know what prosthetic group that each one of these enzymes contains and the reaction that is catalyzed. Now, the pyruvate dehydrogenase component, E1, uses a prosthetic group known as TPP. This carries out oxidative decarboxylation of pyruvate. So we are going to oxidize pyruvate and remove a carbon in the form of carbon dioxide. Dihydrolipoyl transacetylase, E2, uses the prosthetic group lipoamide. This transfers acetyl groups to coenzyme A. Dihydrolipoyl dehydrogenase, E3, uses the prosthetic group FAD. The reaction catalyzed is the regeneration of the oxidized form of lipoamide. Let's look at these a little more closely. We're going to start off with E1. This uses thymine pyrophosphate, abbreviated TPP. This has a thiazole ring, and it is a derivative of the vitamin thiamine B1. It is because of the synthesis of TPP that we need thiamine in our diets. The mechanism of action for TPP is an acidic proton removal. This forms a stabilized carbanion intermediate that can participate in a nucleophilic attack. The thiazole ring of TPP acts as an electron sink that stabilizes the carbanion, thus allowing a stable carbanion to form so that it can participate in a nucleophilic attack. Lipoic acid is actually derived from a fatty acid, octanoic acid, that is an 8-carbon fatty acid. Now, as a fatty acid, it has a carboxylic acid. This attaches covalently to the epsilon amino group of a lysine in the enzyme to form lipoamide. So lipoic acid is shown here. You can see that it is a hydrocarbon with a carboxylic acid on the right, and then it has this disulfide bridge that helps to form a ring structure. Now this is long enough, but when you add something like this to a long amino acid side chain like lysine, you extend the reach of this functional group, the disulfide bridge. This is lipoamide. At the top of the page, we can see the lysine side chain, and lipoic acid is attached to the epsilon amino group to form lipoamide. Now the acyl carrier is actually the reactive disulfide bond at the end. Now we're going to revisit coenzyme A. This is a derivative of the vitamin pantothenic acid B5. Again, this allows for formation of a high-energy thioester bond. The reactive group is seen as a sulfhydryl group on the left. This is going to carry and transfer an acyl group. One of the other cofactors involved in the pyruvate dehydrogenase complex is FAD. And again, this is a derivative of the vitamin riboflavin. This is going to act as an electron carrier. This carrier can transfer one electron at a time at each of these sites. And so this, what we see here, is FAD, and this is the oxidized carrier. When this is reduced, when it is actually carrying the electrons, it is FADH2. This is the cofactor number 5, nicotinamide adenine dinucleotide. NAD+ is the oxidized form that is shown here, and NADH is a reduced form. This is going to transfer 2 electrons and a proton at one time, a hydride ion. This is H-. The first thing that's going to happen is pyruvate is going to combine with a carbanion of TPP. That results in the production of hydroxyethyl TPP plus carbon dioxide. So one of the most important things about this TPP is because the active site carbon is located between a nitrogen and a sulfur atom. It is far more acidic than a regular carbon, and so can lose a proton quite easily. The rest of the molecule acts as an electron sink to stabilize the developing carbanion. And so the mechanism goes like this. First, we have the formation of the carbanion that attacks pyruvate. Once this happens, we end up with decarboxylation, and so the end product is hydroxyethyl TPP and carbon dioxide. And so now we're going to oxidize and transfer the hydroxyethyl portion of hydroxyethyl TPP. We're going to oxidize it and transfer it to one of the sulfurs of lipoamide. This results in the formation of the carbanion of TPP again, and acetyl lipoamide. Please remember that lipoamide is attached to that long swing arm, and this is just the functional group at the end. We now have an acetyl group attached to a long-armed carrier. Now remember, because this is a thioester, that it is a high-energy compound. And it's possible to make this high-energy bond because in the step number 1, we just liberated carbon dioxide. And so we're going to trap the energy that we gained from this elimination of carbon dioxide in the thioester linkage. And so step number 2 is completed. We've transferred the acetyl group to lipoamide. Now we're going to transfer this acyl group to coenzyme A. And this is a simple transfer from one sulfhydryl to another, forming one thioester from another, and so there's no loss of energy. And so we've retained much of the energy that we gained when we lost carbon dioxide to form acetyl-CoA and dihydrolipoamide. Now the problem is that we have 2 sulfhydryl groups on the lipoamide, not the disulfide bridge, which we need to regenerate in order to get a competent enzyme back again. And so we have the product that we want, acetyl-CoA. That was the whole reason that we started out this whole thing. But the problem is that we have dihydrolipoamide as well, and this is an inactive form of this particular portion of the enzyme. We must regenerate the disulfide bridge between these 2 sulfur groups, and so we're going to oxidize dihydrolipoamide to form lipoamide again. To do this, we're going to use FAD. FAD is going to oxidize dihydrolipoamide, and in so doing, FAD is going to be reduced. We're going to end up with lipoamide and FADH2. Now the trouble with this is we have lipoamide, but we also are left with FADH2, and we need to regenerate FAD. And to do this, we use NAD+ as an oxidizing agent. We're going to oxidize FADH2, and in so doing, we're going to reduce NAD+ to NADH and a proton. And with this, we've restored the enzyme to its original oxidized state. First, we have the formation of the carbanion that attacks pyruvate. Pyruvate is decarboxylated to form a 2-carbon alcohol. The long swing arm of lipoamide is going to make a covalent linkage in the form of a thiol ester between the acetyl group and one of the constituents of the disulfide bridge of lipoamide. Now that we have the acetyl group attached to lipoamide, we're going to swing it over to coenzyme A to make a covalent linkage between the acetyl group and coenzyme A. This results in the formation of acetyl-CoA, and that's exactly what we want. So we've done our job. The trouble is, we've broken our enzyme. Instead of the disulfide bridge in lipoamide, we now have 2 sulfhydryl groups, and this is not good. We're going to have to oxidize these 2 sulfhydryls to reconstitute the disulfide bridge so that the enzyme will work again. To do this, we're going to use FAD to oxidize these 2 sulfhydryls. In the process, we're going to make FADH2, and now our enzyme's broken again. We have to fix this by oxidizing FADH2 to FAD to form a fully functional enzyme. The cofactor that's going to oxidize FADH2 to make FAD is NAD+, and in the process, we're going to make NADH plus H+. The reactions that are catalyzed by pyruvate dehydrogenase to generate acetyl-CoA are irreversible. So when you see irreversible, please think regulation. And in fact, pyruvate dehydrogenase complex is highly regulated. The main site of regulation is the pyruvate dehydrogenase enzyme, E1. It is sensitive to intracellular energy charge and is downregulated when there are high concentrations of NADH, ATP, and acetyl-CoA. All 3 of these are indicative of high energy charge in the cell. When there's a lot of ATP, the citric acid cycle will be slowed down. This will result in higher concentrations of acetyl-CoA being found in the cell. And both acetyl-CoA and ATP can downregulate PDH. And NADH is also indicative of high energy in the cell. Because if there's enough ATP, you're not going to be using NADH in the electron transport chain to make more, and so NADH supplies in the cell will be high. With many allosteric regulators that we're going to see in this semester, it's all a question of which small molecule binds first. And so ratios are all important. The ratio of NADH to NAD+ is indicative of energy charge. When this ratio is higher, there's a greater chance that NADH will bind to the allosteric site rather than NAD+. In conditions of low energy charge, pyruvate and ADP will be in higher concentration, and so will allosterically regulate pyruvate dehydrogenase to activate it. Pyruvate dehydrogenase, enzyme 1, is also regulated by covalent modification through a kinase that phosphorylates serine residues. And so, when pyruvate dehydrogenase is phosphorylated, it is downregulated. When pyruvate dehydrogenase is dephosphorylated, it's more active, and there is a phosphatase that removes the phosphate to upregulate pyruvate dehydrogenase's activity. It is important to note that the products of pyruvate dehydrogenase enzyme, acetyl-CoA and NADH, also activate the kinase, and so when these products are in high abundance, they really shut the enzyme down by two ways, both directly through binding to the enzyme itself, allosterically inhibiting it, and also indirectly by activating the kinase that will covalently modify the enzyme and thus inhibit it. Now, several problems can arise that directly impact pyruvate dehydrogenase complex. One of these is thiamine deficiency. This causes beriberi because of a deficiency in the cofactor that works in enzyme 1. Because of this, energy stores in the cell become limiting, and one of the symptoms of beriberi is intense fatigue. In fact, the name beriberi means I can't, because persons who have this deficiency are really unable to get around well and to function. Mercury and arsenite can also impact the pyruvate dehydrogenase complex, but do so by inhibiting E2. These two can bind to the sulfhydryl groups and thereby inactivate lipoamide. Now, there are ways to counter this, and one of them was used in World War I, in which arsenic was used as a component of gas that was used as a chemical weapon. To combat that, British soldiers were given 2,3-dimercaptopropanol. This is known as BAL, B-A-L. Now, this small molecule has two sulfhydryl groups of its own and can outcompete the arsenate from dihydrolipoamide. The arsenite chelate of 2,3-dimercaptopropanol can be safely excreted.